Most of the substances of our Earth are in the form of mixtures. But there's one special kind of mixture that has far more importance than any other. The oceans and seas of the Earth are vast solutions, and microscopic living cells are tiny sacs of them. Many of the processes of life occur in these homogeneous mixtures we call solutions. In simple organisms, in the cells and tissues of complex organisms, solutions make possible the chemical interactions that provide food, carry off the wastes of metabolism, and transmit nerve impulses. Solutions are indispensable to cooking and to tasting and eating. And in the laboratory and industry, solutions not only make the measuring and dispensing of chemicals convenient, but speed chemical reactions, and in fact make reactions take place that would not otherwise occur. Why? The answer lies in understanding what solutions are, and perhaps what they are not. A scoop of clay, a little shaking, and we have what seems to be a homogeneous mixture. The clay and water mixture is a suspension. In a suspension, the particles that form it are big enough to be seen with the naked eye, big enough even to be filtered out easily. But given time, the clay particles will settle out. The substances that make up a solution never settle out. The mixture is always homogeneous. This time, we add a little powdered gelatin. Now we can't see any particles, just an overall change in color. Again, the mixture looks homogeneous. If we give it as much time as we gave the clay mixture, nothing will settle out. Of course, the gelatin itself might set, but watch what the effect is when we shine a light through the gelatin. You can see the light as a beam because particles in the gelatin are large enough to reflect and scatter some of the light waves, even though the particles are not big enough for us to see. Those particles in the gelatin are the cause of this Tyndall effect. But this never happens in a solution. A light beam is not scattered in a solution. The gelatin and water mixture is a colloid. But if we take a beaker of water again, and this time a scoop of common table salt, and mix them, this time what we get is a true solution. A homogeneous mixture of substances of molecular size or smaller. This one happens to be a solution of a solid in a liquid. Solids dissolved in liquids are essential for the life processes of living things. Blood, 90% water, transports materials throughout your body. Dissolved in the liquid portion of the blood are formerly solid substances that are being brought to your cells as nutrients, and wastes that are being carried away. Solids dissolved in liquids are the most common types of solutions. But solutions aren't limited to that kind of mixture. Some solutions are homogeneous mixtures of gases in liquids. Carbon dioxide gas dissolved in water gives soft drinks their fizz. Oxygen gas dissolved in water is essential to plants and animals that live in water. And organisms like us, who live out of water, depend on oxygen dissolved in other gases. This mixture we call air is a solution of gases in gases. Alloys begin their existence as solutions of liquids in liquids. Steel, for instance, is formed from a solution of various molten metals like manganese, vanadium, and tungsten, dissolved in iron. But when most solutions of metals pass from their liquid phase to their solid phase, in other words, when they solidify, they lose their homogeneity. Most alloys, like steel, are heterogeneous mixtures. Solutions, when they form, they flavor our soup and carry on our life processes. But what exactly happens when a solution forms? To see, let's go back to the simplest and probably the clearest illustration, the saline solution, the solution of ordinary table salt in water. Salt, sodium chloride, is a crystalline ionic solid. Each crystal is made up of a regular arrangement of charged atoms, ions of sodium and chlorine. Attraction between the negative and positive ions holds them all together in ionic bonds and creates crystals of the ionic solid sodium chloride. Water is a molecular substance, not ionic. Two atoms of hydrogen bond covalently with one of oxygen to form the water molecule. The bonds have great strength. The molecule is electrostatically neutral, but extremely polar. Because of an uneven distribution of electrons in the molecule, the oxygen side has a partial negative charge, and the hydrogen side a partial positive charge. The liquid, water, is made up of great numbers of such polar molecules, held together by electrostatic forces of attraction between the positive and negative poles. These connections are easily broken and reformed, giving water molecules great mobility in the liquid phase. So we have two substances with charged parts: water, made up of polar molecules; salt, made up of charged ions. And we mix them. All we can see is the apparent disappearance of the salt crystal. But the disappearance is being caused by profound changes in the basic structure of the salt. When the salt enters the water, the negative chloride ions attract the positive side of water molecules. They can overcome the strong attraction of the oppositely charged sodium ions and pull the negative chloride ion out of the crystal. And the same sort of attraction takes place between the positive sodium ions and the negative side of the water molecules. So the ions in our crystal of salt dissociate. In time, if the salt completely dissolves, each ion becomes surrounded by a number of water molecules. This is called hydration. Now, as the ions are pulled out of the salt crystal by the water molecules, they will not stay concentrated in one part of the water, because molecules of a liquid are always in motion. When we look through the microscope at tiny particles suspended in a liquid, we see that they have a zigzag motion. This is called Brownian movement. The particles are actually being struck by water molecules in constant, irregular, and rapid motion. We can't see the molecules, but we can see the result of the collisions. Molecules of all fluids move in this way. So this movement of water molecules disperses the sodium and chloride ions throughout the water. Sugar crystals dissolve in water too, but sugar is a molecular substance, not ionic. So when crystals of sugar break apart, whole molecules of the substance disperse. So now, with the dispersion of molecules or ions throughout the water, we have a solution. And now we need some terminology to work with. The salt, the substance that dissolves, is called the solute. The substance that causes the dissolving is the solvent. When a solid dissolves in a liquid, the liquid is always called the solvent. In other kinds of solutions, the substance in the greater quantity is called the solvent. In air, nitrogen is the solvent, and oxygen, argon, water vapor, and other gases are the solutes. Water is the solute in rubbing alcohol, and the solvent in our saline solution. Water is actually the most common solvent there is, and undoubtedly the most important. In all living things, water is the transport medium for the dissolved substances that sustain an organism's life. Because the materials that the water transports are of molecular size or smaller, they can pass through the membranes that hold the larger constituents of cells in place. Important food materials like glucose and amino acids are transported through living organisms in their molecular forms, pass into cells, and react slowly with oxygen and other substances there. Now, more terminology. Notice the terms added to these chemical descriptions. Some of the solutions are dilute. Some are very dilute. Some are concentrated. These terms tell us, very generally, something about the relative amounts of solute and solvent. For instance, concentrated sulfuric acid is 96% H2SO4 by weight and 4% water. Concentrated hydrochloric acid is only about 36% hydrogen chloride by weight and 64% water. The term concentrated simply means that there is a relatively large amount of acid. All dilute means, generally, is that there is less solute than in a concentrated solution. A very dilute solution is almost pure solvent with just a very small amount of solute. A way of talking about the concentration of a solution more precisely is to use the concept of molarity. By definition, a mole of any substance contains the same number of units of that substance, 6.02 times 10 to the 23rd. In a mole of carbon, the number of atoms is 6.02 times 10 to the 23rd. In a mole of carbon dioxide gas, the number of molecules is 6.02 times 10 to the 23rd. 1 mole of sodium chloride contains 6.02 times 10 to the 23rd sodium ions, and the same number of chloride ions. Molar concentration can be used as the basis for comparing solutions. The moles of solute per liter of solution is a solution's molar concentration. The higher the molarity, the more concentrated a solution is, the more particles there are per unit volume. The more reacting particles of solute there are, the more individual reactions can occur in the same volume. It's these particles of the solute that also affect the properties of the solvent. Water, for instance, freezes at 0 degrees Celsius. As water molecules lose energy, they arrange themselves into an orderly crystalline structure, ice. But the particles that form a solution interfere with this process of crystallization. The effect is that the solution freezes at a lower temperature than the solvent does. A solid solute like salt has the opposite effect on the boiling point of a solvent. This pure water and this saline solution are both at the same temperature, yet the water is boiling, but the solution isn't. The boiling point of the solution has been raised. More energy will have to be absorbed by the solution before it will boil. So adding a solute to a solvent changes the solvent's properties. Can solute be added indefinitely? So far, all the salt we've added to the water in the beaker is dissolved. But as salt goes into solution, some sodium and chloride ions keep coming out of solution, recrystallizing. Because the rate of ions going into solution is greater than the rate of recrystallization of the ions, the concentration of the saline solution keeps increasing. But gradually, as concentration increases, the rate at which the solute particles go into solution becomes equal to the rate at which they're coming out of it. A state of equilibrium is reached, and the solution is said to be saturated. Saturation is the condition now of our saline solution. It will not hold any more dissolved salt in this amount of solvent, as long as the temperature of the solution stays the same. But if we raise the temperature of sodium chloride in water, more solute can dissolve. This is not true of all solutions. In some cases, the opposite actually happens. But now our salt solution is unsaturated again, and more particles go into solution than come out of it. We can dissolve more salt into our solution until equilibrium is again reached and the solution is saturated. Adding solvent would have the same effect. The more water, the more salt we can dissolve into it until saturation is reached. But under certain conditions, it's possible to go beyond saturation. This is the condition of this sodium thiosulfate solution. It is supersaturated. There are more particles of solute in it than a saturated solution of this solute can hold with stability. But the particles are unable to take on the crystalline arrangement of their solid. They need some particle, even a bit of dust, to start settling out on. But there isn't any. Now watch. A tiny crystal of the solute provides a kind of trigger to start crystallization. Now the excess solute can crystallize out, and the solution can return to a saturated equilibrium. This is not usually the way solutes precipitate out of solutions. If we just reduce the amount of water in our saline solution by allowing it to evaporate, the solution can hold less and less solute until finally the solution becomes saturated. And as the water keeps evaporating, the salt crystals precipitate out. Nature frequently operates in the same way. Salt in a great underground mine, left behind when a prehistoric sea dried up. Raw sugar is produced commercially by an evaporation process that separates crystalline sugar from the water in sugar syrup. Unfortunately, what nature doesn't do is make all things easily soluble in water. Oil, for instance. Oil hardly dissolves at all in water. And neither does carbon tetrachloride. And yet, oil dissolves quite easily in carbon tet. Salt, on the other hand, which we know dissolves easily in water, does not dissolve significantly in either oil or carbon tet. Here's why. Remember, water is a polar molecule with a positive and negative side. Salt is an electrolyte, a solid made up of positive and negative ions. Salt dissolves from the attraction between the salt ions and the water molecules. The salt actually pulls the water molecules away from each other, while the water is pulling apart the salt. Though oil is a molecular substance like water, it isn't polar. Water attracts other water molecules much more strongly than it attracts oil molecules. If an oil molecule gets between two water molecules, the water molecules come back together again and squeeze the oil out. So oil doesn't dissolve significantly in water. But carbon tetrachloride, like oil, is a nonpolar substance. The attractive forces between carbon tet molecules, between oil molecules, between carbon-tet molecules and oil molecules are all about the same. So the molecules of both substances tend to slip between each other until the distribution becomes random and homogeneous, and a solution is formed. In general, solvents are more likely to dissolve solutes with similar characteristics. So nonpolar solutes dissolve in nonpolar solvents. Ionic and polar solutes dissolve in polar solvents. And generally, this combination is the one more significant to us, particularly when it involves ionic solutes, because ions can transport electric charges through a solution. The processes of life depend on this flow of electric charges carried to and from all parts of our body by the great transport medium, water. From the homogeneous mixtures that bathe and feed our tiniest cells, to the homogeneous mixture, the sea, that covers 3/4 of our world, solutions are an intimate part of life and fundamental to the life of our planet.